So this is the second lecture. I think I should start with screen sharing with you. So yes, I understand that you can see my screen now, and in the previous lecture, I just outlined the course and discussed a few fundamental things about geometric constructions. Now, in this lecture, we will concentrate this way in the standard basic definitions and fundamental concepts. Okay. So, the formal definition of a mechanism is given something like this. A mechanism is an assemblage of interconnected bodies that move through well-defined relative motion. Now, the three underlined terms, bodies, which will actually give you the definition link very soon, and interconnected. Otherwise, it will be like studying the motion of several bodies separately, which is not the idea of this subject matter. Okay. Interconnected bodies. And it is a relative motion that we study. Whether the entire mechanism is going from here to moon is not of our business. That somebody else in some other subject will study. We only can do that under the banner of another subject. That's a different thing. But in this matter, the mechanism will talk about just this, relative motion. And this actually makes the preliminary notion of nothing going wrong if you consider one of the bodies as fixed. Okay? And that is what we will end up doing in our actual day-to-day business. Now, there is a term called link. A body in a mechanism contributing an element to a kinematic pair, which is a connection. Now, I have written rigid within parentheses, basically to indicate that you can have a mechanism with flexible links, but most of the time, under the rubric of this subject, when we study mechanisms, we study them as composed of bodies which are rigid. And rigid also in what sense? That whatever little deformation goes on, that is insignificant for our practical purposes. Okay? So, in that sense, you have this. However, I caution you that when some of you do some advanced studies in the mechanism, then you will find flexible link mechanism also. That is a great field of study nowadays. But right now, don't bother. Right now, most of our links will be rigid. And whenever we have bodies which are not rigid, like rope or whatever, so that segment of the motion and force transmission has to be handled appropriately according to what we know otherwise from basic physics. And there we do not go into huge details because that is a subject matter of another course, another subject. Now, links. What kind of links we will have? Actually, it is based on the connections. Okay? And a link which is connected to only one other link is called a unary link. Hosh and Malik also define it as singular link. Okay. Actually, both the words singular and unary in this context are a little forced use because no exact place filler was available. So this is in one way awkward or special use. This is in another way awkward or special use. So you choose whichever you like. Authors of your book prefer singular link, I prefer unary link because singular is a word which I consider with very deep understanding, deep notion. Okay, something peculiar and something perhaps terrible going on there. So a link connected to only one link is nothing of that special sort. Okay, at least not to people of this time. Okay. Binary. This is a very common thing for people old and new, everybody. It is a link which is connected to two other links. Okay. So for kinematics purposes, we can consider one at this end and the other at other end. However, the physical extent of the actual body may go beyond that in order to fulfill some practical task. That's a different thing. So we are not talking about physical extent for that matter. Similarly, you can define ternary link connected to three others, quaternary link connected to four others, and so on. And sky is the limit. You can have canary link, which you write like this. And say whatever way you can say. I said canary, which is very awkward, which is very funny, but that's how it is. So there is no limit as such. And then we have already used the word kinematic pair, and now here we define it. A kinematic pair, it is a connection between two bodies or links permitting relative motion. Okay. Now, why did not they simply call it joint? The reason was that when people formalized this subject, by that time the word joint was used for all sorts of things for a very in a loose sense, and they wanted to make formal definitions very clear and perfect and meaning what they want it to mean and nothing else. So they defined it as kinematic pair. This is the term they coined, the old grandmasters. Okay, and the idea of pair is, for example, consider one body moving relative to another. The first body contributes a part of it as a slot in which the other body contributes a part in the form of a peg which is capable of moving in that slot. So this body contributes this surface as an element. Okay? And this body contributes its inner surface as an element. So these are two elements, and together one of the elements can rub against the other, and that makes it a pair of two elements. And in that sense, it is a pair. Okay, so it's a kinematic pair in that sense. Okay, so connection between two bodies permitting relative motion. Even if one body is over another body and capable of relative motion, for example, you see this body and touching this body, and if this is a motion possible between the two, then this is again in its own way offering a pair. Okay? So it's a very precarious kind of connection, but it can be. Okay? Now, related to kinematic pairs, you have important definitions, important terms. First, degree of freedom of a kinematic pair. As with any degree of freedom in any context, it is a number of independent coordinates to describe the relative motion completely. Relative motion between the two links. So whatever will describe that relative motion completely, that is the degree of freedom of the kinematic pair. And those variables, those coordinates will be called the pair variables. Okay? So what kind of situations may arise? May arise in the sense which are used in engineering. So you have a little classification. To begin with, people have thought of classifying kinematic pairs between lower and higher. Lower is ordinary kind of contact, okay? Like this, the example that I gave you. This has a surface, this has a surface, and they contact just like that. Okay? So it is a lower order of contact, ordinary kind of contact. Okay? So an area contact between the two elements of the two links give you a lower pair. On the other hand, a line contact like this, or if you put a ball over this surface, okay, then a point contact, they will be precarious kinds of contacts which are higher order. Like, you are not very keen to agree that they are nice proper contacts, but contacts they are. So they are higher order contacts. So based on that, you call such pairs, such kinematic pairs, as higher pairs. And then, as an afterthought, wrapping pair was also included because some connections between elements were involved in actual engineering practice, which are actually neither way, clearly. I mean, they could be line contact, they could be area contact, but something was fundamentally different. Okay, and that is like belt or chain or rope, which wraps around the other link. Okay, so a belt or a rope or chain wraps around the surface of the other link. Okay? So such pairs are called wrapping pairs. We also give area contact for that matter, mostly area contact. It is possible to, you know, critically make some sort of line contact, but typically it doesn't work properly during operations. Now, these are special and to be treated specially. Lower pairs are in use widely and they are of several kinds. First of all, revolute pair. Okay. The symbol is R and it has 1 degree of freedom. So if this is one element of one link, one contributing link, and this is another, and the relative motion allowed is this turning, okay, relative turning, then this is called a revolute pair. Okay. You could call it rotary, but revolute is the standard name. Similarly, if the relative motion is like this, sliding, okay, and not rotation, only sliding, okay, then that kind of a pair is called prismatic pair. As if this is a cross section of a prismatic body and this is prismatic hole and this is a cross section of another prismatic hole and they can only slide. You know why it is called prismatic? So the connection does not have to have that polygonal shape. Is that the polygonal shape properly and perfectly stops rotation? This circular shape will not properly stop rotation. In principle, rotation was possible. It would not be clear. So prismatic makes it very clear. Whatever be the actual shape, the sense of the motion is that only relative sliding is possible, no rotation is possible. Fine. So this is the symbol is P because it is prismatic. Degree of freedom is again 1. In this case, degree of freedom is that variable is theta. Relative rotation is possible in revolute pair. In the corresponding prismatic pair, it is a relative linear position displacement or the corresponding position is involved as coordinate. That is, I am denoting it as x. Fine. Now you can have a screw pair, okay, or helical pair, and for that the symbol used is H. Okay, so the relative motion is on a helix. Okay, true, as you know. And here you can take either theta or s or anything proportional to that as the relative, as the variable, as the coordinate describing the relative motion, and they are related like this. Delta theta by 2 pi is the corresponding delta s by L, where L is the lead of the spool. That is, in one complete turn, how far it advances along the axis. But degree of freedom is only one. So there is a theta motion, there is an s motion, but since they are related with through a relation like this, so degree of freedom is just one. Independent, only one. If you have both of them free, independent of each other, then you have a cylindrical pair for obvious reasons, and the symbol is C. So it has 2 degrees of freedom, both theta and s, which can be independent. Such joints, such pairs are also used. And then there is a pair called planar pair. Okay. So one body in a plane contact with another and capable of moving relatively along x, along y, and along and can rotate about an axis perpendicular to that plane. So basically, related to that plane, this lamina has complete freedom. However, it cannot go out of that plane and it cannot turn any other way. Okay, because then one end of it will hit, another end will lose contact. Okay, so for this, people wanted a symbol, and they could not use P because P was already reserved for prismatic pairs. So they used E. You will ask why E? Now the German word for plane is Ebene. Okay, and Germans and Russians originally contributed enormously in the development of this field. So once in a while, some German terms appear in the picture. Okay. So planar pair was considered Ebene. Okay, E. So the symbol is E. Degree of freedom is 3. Sx, xy, theta. Fine. Then there is a spheric pair or spherical pair, as you can say. Basically, this is a ball and socket. Okay, and the symbol of that is S, and this is one reason why screw pair was not called S, because S was reserved for spheric pair, and this has 3 rotational degree of freedom. So one ball sitting inside a socket, and about all the 3 mutually perpendicular axes, they can execute relative motion. This fellow can stay in its own orientation, and this fellow can go on turning about all the 3 axes. Okay. So this has 3 variables. How you parameterize them, how you describe the independent rotations, that is up to you. Okay. So there are many possibilities of describing the rotations, complete rotations, through 3 independent variables. Now, as I told you that several kinds of things were classified as joints, so people wanted a word other than joint to classify technically what they wanted, and so they called it pair. So now, because an example of that is, you would think of, you saw rotary joint, sliding joint, ball and socket joint in the technical scholarly terms. You would think, where is universal joint? It's not there. There is no corresponding word here, because universal joint is actually a sequence of 2 revolute joints with concurrent axes. Ball and socket joint or a spherical pair can be modeled as 3 concurrent revolute pairs, or actually can be engineered in the form of 3 such angles if you have the intention of manufacturing fabricating, manufacturing it, and actually assembling it in a mechanism and using it, as we do in robotic race, but it doesn't have to be so. Okay, there are proper ball and socket joints which are in no way a sequence of three concurrent successive revolute pairs. So universal joint does not have a counterpart in this classification of kinematic pairs. Now see some pictures. This is straight from the book. So this is revolute pair. One body is contributing this rod, another body is contributing this hole. Their mating surface is the cylindrical surface, but along that cylindrical surface, the axial motion is blocked by this and this, and so only relative motion possible is this turning, and that is revolute pair. Similarly, you see prismatic joint, prismatic pair. So only motion possible is in and out. So this is S. Then helical pair H. Okay, screw. This is the S, and this is the theta, and the relationship is governed by the lead. This distance. Okay. Here both the axial translation and rotation are independent. So it's a cylindrical pair, and this is the typical ball and socket joint. Okay. Correspondingly, steric pair. So one side of it has been cut to show you how it looks inside. Okay. And this ball can rotate in all possible ways inside the socket without going out, because more than half of it will be actually inside as you supply this quarter also. Now this is a planar pair. Okay. So in which this body can move in x direction as well as in y direction, and as well as and in theta direction also, theta sense also, rotation also. I will say that for that matter it can go out of business, go out leaving the contact. But understand, this is just a schematic. It may be that the forces are all downward, so it will not go out on its own. There is another possibility: the pair remains same, even if just above this height there is another part of the lower body, body 2, which encloses it inside. Okay, it can be that there is a planar slot in which this body is sitting like this, and it can execute all motions inside, but it cannot come out. That is possible, and so it cannot rotate either. That is anyway not possible. Okay, so these are the 6 lower pairs. Higher pairs: cam and follower, the gear teeth, 2 gears. So those you will encounter towards the end of the course. Now this is an extremely important definition: kinematic chain. An assembly of links connected by kinematic pairs is called a kinematic chain. Okay. And you call it a closed kinematic chain if every link is connected to at least 2 other links. Okay. No unary link. Okay. So, for example, see, this is an example of a closed chain. Link 1 is connected to 257, 2 is connected to 1 and 3, 3 is connected to 2 and 4, 4 is connected to 3, 5, 6, and so on. Okay, so every link is connected to at least 2 other links. Okay, 2, 3, 5, 6, 7 are connected to 2 other links. 4 and 1 are connected to 3 other links. On the other hand, an open chain can have a unary link. Actually, it must have a unary link, otherwise it will fall here. In this, you see, link 6 is a unary link, a dangling link at the end. And in modern applications, this has quite a bit of utility. Okay, so for a robotic hand, at the end you may have a link which just has the hand, and of course you have to put a motor here. So in the earlier version of mechanism theory, the 19th century stuff or the early part of the 20th century stuff, these kind of things were typically not studied too much, but now we study them a lot. Now there is another term called simple kinematic chain. All links are binary, and that means what? With link 1 you connect link 2, with link 2 you connect link 3, and like this. If you have to go all the way to connect the last link to the one again, and that only will give you a kinematic chain with all links binary, and that means it is a single loop. You see, in this case there were 2 loops, 1 loop and 2 loops. Here also, in a way, it was 2 loops, 1 loop and 1 incomplete loop. Okay, it remains dangling open because it was open. Okay. So now this I consider this definition itself, open kinematic chain, no sorry, simple kinematic chain. In our time, actually there is no need to define something of that sort only in this sense. All links binary. Okay. You just say, I mean it's enough actually. All single loop mechanisms. You don't have to say all links binary. But the time when this subject really developed properly, at that time they were, intensively preoccupied with closed kinematic chains, and simple kinematic chains were not really given that much importance. But in our time, they are given. Okay. For example, you could simply say that all single loop chains, whether it is closed or open, you don't bother. It can be open. Who cares? Say link 1 is connected to 2 only, 2 is connected to 1 and 3, 3 is connected to 2 and 4, and so on till n. Now this is our idea of chain. So you could include actually all such mechanisms, all such chains also among simple kinematic chains. You simply define them as single loop. The loop may be closed, which this definition means, which this term means, or the loop may be open, in which case you will have 2 unaries at the 2 ends. That should be perfectly valid. Okay. In fact, most robots operate on that simple kinematic chain. That is actually simple so far as robotic mechanisms are concerned. Then another definition, which was an enormously important definition in the old school of thought, is constrained kinematic chain. Okay. Constrained in what way? Relative position of one link, just one. One link determines that of all others. That is configuration of the entire chain. That is, if you specify one relative motion, that is between link 2 and link 1, or some such pair, then that itself will determine all the corresponding relative motions. That was classically defined as constrained kinematic chain. Constraint means what? Through one input, you constrain it. Now, why I say that it is not really so needed, because if you have the need of defining two such relative motions to determine all others, then what? Nothing goes wrong. Through those two inputs, you constrain the mechanism, you constrain the kinematic chain for a given complete relative motion. So the thing is that this is actually a result of the historical development of the field. What it means simply in our ground truth sense is what was defined as constant kinematic chain and as used in these textbooks, old style textbooks, are simply single degree of freedom chains. Okay. At that time, they did not study extensively multi-DOF chains because multi-DOF mechanisms, executing them, analyzing them, using them was in several ways difficult from the theory point of view as well as from the technical implementation point of view, the engineering point of view. You did not have that kind of control systems also. Okay. Controllers were also very basic and primitive. Okay. Anyway, so this is what textbooks, old textbooks, define as constraint kinematic chain. We will encounter many times multi-degree of freedom chains and use them happily. So let us not be very bothered about this, but you should know what was the sense of some old author saying something, okay? Because that you should know, otherwise you will not get the sense correct. On the other hand, you should also make proper note of the you know dissenting tone that I am offering you in making light of these so-called strict definitions, because you should also understand clearly what an author means if that author wrote his piece in last 40 years. Okay, I went through my training in these last 40 years, and so I understand the language of this time quite well. So that is why I am putting these dissenting notes so that you do not take these things very critically in your heart, but you should understand, you should know the sense of the original definitions. And I'm also going on giving you the historical perspective at the appropriate moment so that you don't consider them totally wrong or this totally wrong. Okay, so there is a meeting ground to the historical development over the years, over the decades. Now, mechanism. You at this point you can define a mechanism after having gone through several technical terms. A kinematic chain with one link fixed. And this is where we have been heading all the time. We have been talking about kinematic chain for quite some time, all kinds of them. Okay. And we have already said that the entire business is basically geared towards the relative motion. Then why not fix one of them and then study the rest of it? So fine, so you fix one of them, then actually it becomes a usable artifact. And typically in engineering practice, in ordinary engineering practice, that fixed link will be the art, right? Why I corrected myself and said ordinary engineering practice? Because in another practice, which is not so ordinary engineering, it is a mechanism on a space vehicle. Space vehicle will be that fixed link, relative to which everything else you will be describing. Aircraft also, for that matter. Okay. So now the textbook actually defines it as a closed kinematic chain with one link fixed. Now, this is one point where I would not take it sitting down anymore. Okay, so it doesn't have to be closed. Okay, it can be open kinematic chain, because I mean last 50 years people have talked about robot mechanisms, and they are mechanisms enough. Okay, and they follow a lot of theory of the rest of the mechanisms under within codes, but they are open. Okay, for a robotic mechanism, you have to have an open chain. So this closed is actually unnecessary import. For that matter, Professor Malik also says, after telling quite a few terms and technical terms and definitions, as I have told, at this stage, a mechanism can be defined more rigorously as a closed kinematic chain in which one link is fixed. I had some discussions with him, and he said, "Okay, yeah, but anyway." So it is a little loose business. You keep your mind clear that the mechanism doesn't have to be closed. But what the classical field studies at length intensively is typically closed kinematic chains. Okay, but it doesn't have to be so. Now, another definition: linkage. A mechanism having only lower pairs. That kind of a mechanism is called a linkage. And here you have to exercise caution, because these pages of any textbook of a subject require reading through line by line carefully, reading them several times, underlining them and putting them firmly in the head and so on. Because otherwise, people quickly see them and then come across only linkage mechanisms for say 2 months. And then when a cam mechanism also they encounter, they say that in this linkage, we have a cam and we have a follower. You can't have that. If you have a cam and a follower, it is not a linkage mechanism, it is a cam mechanism. So a linkage is a mechanism having only lower pairs. So keep that in mind. So do not misuse the word linkage. I have heard some people doing it. It hurts. Now, planar mechanisms. This is another important term which we should be clear about. Clear about in all senses. Here also, I have heard people telling somewhat wrong things, which damages the concept. A mechanism is called planar mechanism if all points on every movable link move in parallel planes, not in the same plane. Many people quickly say that all points move in the same plane. No, 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 no. Doesn't have to be. The bodies are rigid bodies having quite some kind of thickness, and if all were moving in the same plane, then the motion of one would obstruct the other. Okay, so all points on the movable links move in parallel planes. You see, they are moving in parallel planes. Okay, what is so special about that? First, understand how do you get a planar mechanism, and then what is so special about that? Why are we so happy about having some mechanism called planar mechanism? So, axes of all the revolute pairs in a planar mechanism will be parallel. So then this body will move like this, rotate about this axis. This body will also rotate about another axis which is parallel. So all points will move. Say if you consider the coordinate along this direction of the common axis, along the common direction of the axis as z, and you say z coordinate of all points will be fixed. I mean, this point will have its own z coordinate, this point will have its own z coordinate, and so on. Okay. So that is how it is. Fine. So all the revolute pairs will have their axes parallel, and the direction of all the prismatic pairs will be in a plane or in a parallel plane. Okay, that is, the directions will be all perpendicular to this common direction of the parallel axis, and that is how all points will move in parallel planes. Fine. And more special, only R and P pairs were pointed out here. Other lower pairs will not be possible. You can have cam, okay. You can have gear. There is no problem there. Now, no helical pair is possible, no screw pair, no cylindrical pair because you cannot ensure this condition. Spherical pair, no, no cylindrical, no spherical. And even E pair, planar pair is possible, but it is absurd because what relative motions are possible at all between two bodies in such a mechanism? Fx, Sy, and theta. In order to have all points move on parallel planes, there is only three motions possible, only three relative motions possible, and an E pair freely offers all the three. So, whatever motions are possible in planar, whatever relative motions are possible in planar mechanism, all of those motions are actually allowed in a planar pair, and that means there is nothing to study in it. Okay, so you can, I mean, there is no constraint. It's just like a free body. Okay, for a planar purpose. Fine. So even an E pair is absurd. Among lower pairs, you can have only R and P, and this will be the conditions. So this is a planar mechanism. And the main thing about a planar mechanism is this observation. Analysis possible in one plane. So if Z coordinate of each and every point of each and every link is on its own going to stay constant, then you have no botheration about analyzing it and finding it and studying how does it change, because it does not change. Okay, so analysis is possible in one plane. So if you make a diagram or take a picture of the whole thing, the entire mechanism moving from a direction along the direction of all those revolute pairs, then in this view you will be able to see everything that is kinematically relevant. That is talking about relative motion, relative positions. Everything is visible in one view. Okay. So if the bodies are moving relative to each other on a table, then you take a picture from the up, that direction, from the top you take the picture and you will see everything moving on the table. Okay. So one view is sufficient, and that means you can show things on a diagram, and therefore graphical methods have enormous utility. And graphical methods were the most potent methods in the early study of the field, because complicated mathematical artifacts, numerical methods, and much more importantly, modern computers were not there at that time. Even though there were numerical methods, even though mathematical artifacts people were developing, the pioneers like Newton, Leibniz, and others, okay, Euler, they were developing methods. But who will sit and do so many addition, subtraction, calculation, multiplication, division, taking logarithm? I mean, anybody would go mad. They were still doing that. So at the time, graphical methods were actually enormously advantageous in cracking a lot of theory behind it, develop a lot of theory behind it, carrying a lot of histories. Now, also graphical methods have utility, but in easily understanding the thing and depicting the thing and explaining it to people. So far as solving problems to get the values of certain things, numerical analysis has far outstripped graphical methods in several dimensions, several senses. Okay. Still, the graphical methods are very important that it gives you a picture, it gives you a sense, it gives you the most important understanding from which you can make sense of the numbers that will be bulged out of your computer program. Okay? Without that understanding, without that sense, computation and results will be just garbage in, garbage out. Okay? So that is why both your instructors put enough importance on the graphical methods, and you are required to do it thoroughly, properly. Okay? And when you use graphical methods, there are a few notations and symbols and conventions that you need to use. We will be talking about them next. You have graphic kinematic diagrams. Now, several kinds of diagrams we will be using. The most basic diagram is the diagram showing relative positions of the different links. And the term kinematic diagram has mostly captured the sense of the diagram showing relative positions of the mechanism. In another way, it shows you completely one configuration of the mechanism at one time. Okay? Another configuration, you may have to draw another kinematic diagram of the same mechanism, another configuration. By turn one of the links by 3 degrees, everything else turns a little, and the resulting thing is another configuration, which will be the subject matter of another kinematic diagram. So these individual diagrams are actually configuration diagrams or position diagrams. Similarly, you will have velocity diagrams and so on. But when you simply say kinematic diagram, then you typically mean position diagram. For velocity diagram, you have to say. Okay. Now, in this, you see all the kinematic features are important. Physical extent, not important. Right? In some problems, you will be shown the physical extent, or you will be showing because that is important for the purpose of the mechanism, even though not a kinematic feature. Okay. So notations and conventions. For that, the simplest thing for me is to take you to upper half of page 10 of Professor Mallik's book. A fixed link which makes a chain a mechanism when you fix one of the links is typically shown like this. This hatching, a little hatching at some place of it is important. And if it happens that in a mechanism, the fixed link appears and in 4 or 5 different points, in each of these regions, a little hatching is given to show that all these distant points are actually the part of the same link, which is a frame, which is a fixed link. Okay. Now, revolute pairs are shown in these ways. This is a revolute pair. Okay. One link can rotate relative to the other, and this is the way to show it. Here it is a single link. Okay, just the shape of the link is this. Now, this shape is important for some business. For example, this part of the link is perhaps going in some slot, so it must be in that direction. And this part has some other duty, so it must have that direction. So in order to preserve both the directions, you have to show it like this. Okay. So what you do? You do not put this little round thing because it will actually show revolute joint. But if you simply make this and this, okay, then you would be actually creating a confusion of this revolute pair being there and you not showing it by mistake or by slip or something. To indicate that it's not a slip, it's a part of a single link, you fillet this region. Okay, and that makes it a rigid body in depiction completely. Similarly, from a running link which has perhaps some connection here and some connection above, much above this, if a branch of the same link, the physical shape of the body, goes like this to connect to something else. How to show that? You show by the center lines, and then to show that you have forgotten nothing, both sides it is the same link, all three sides it is the same link, you fillet it on both angles, at both angles, this obtuse angle also and this acute angle also. So now nobody can be confused that it is two links or three links together. Okay? Now this, when you make this, you want to make many things clear. Okay, so this is a running link in which an interloper link is coming. Keep note, interloper is just a word which I am humorously using. Don't use it as a technical term. Okay, so and connecting it here. Okay, so for example, this long link, mainline link, may be actually a ternary. Okay, it has one connection near the top, another connection near the bottom, and one middle connection. Okay, so to show this, ensure which is the ternary. For example, if you had brought one line from the lower side and connected it to this little circle, another from the upper side and connected it to the circle here, then it would look like three links. One this, another this, another this. In order to indicate that this lower part and this upper part are part of the same link actually, you make it like this. Now this is a typical representation of a prismatic point. Sliding is possible. So that is very simple. You make a slot, I mean this or this, either way. You make a slot in which you show a direction clearly by this kind of parallel lines, and in that just tap another body through which you can have another pin joint like this and bring out something or whatever, and whatever you do, but this is showing one link sliding related to the other slot link. And kinematically, it would mean the same thing if this is made like a little block and this guy is made like a slot. It would technically mean the same thing. Okay? Now this is something important which you do for ternary, quaternary, and higher connection links. Okay? You do not simply make the polygonal kind of representation with little circular joints. You put some shading, either dots or hatching inside, show that all these four corners, the entire body is rigidly connected, it is part of the same link. Okay? And in the case of a triangular link like this, I mean triangular, what I mean is a ternary link like this, if you don't do this, then a single ternary link will give the picture of three binary links. So kinematically, it will not matter much because a triangle is a rigid structure. Okay, without changing the length of a triangle, you cannot suddenly change the triangle itself. You see, three sides of a triangle in a way define the triangle. So, but with a quaternary link, it would make a lot of difference. If you don't give this shading, that would mean that these are four links and not a single link, and that would make a lot of kinematic difference. Because you see, without changing the lengths of the four sides of a quadrilateral, you can happily change the shape of the quadrilateral. Okay, so that will be dangerous kinematically. Fine. In the case of triangular ternary links also, it will be a botheration because it will make many calculations regarding mobility and degree of freedom go a little funny way. Okay, and what one person is telling, the other person will not understand, and so on. So it is better stated. In this case, it would make lots and lots of terrible differences. So I'll for half a minute go back and close with this one little comment, one little term, which is very rarely going to appear in our discussion in this course. For a kinematic pair, you talk of closure. What kind of closure? How the contact is maintained. Okay. So there are two ways of maintaining contact between two bodies which are contributing elements and forming a kinematic pair. One possibility is geometric constraint, the way we discussed revolute pairs and prismatic pairs, cylindrical pairs, screw pairs, spheric pairs, and so on. And these are called geometric constraints. And the kind of closure is called form closure, because due to the forms of the two elements of the two links, the contact is maintained. Okay? The loop remains closed. It is also possible that such a thing is not there. Okay, the form does not ensure the contact, maintaining of the contact. Okay, and in that case, an external force is required. On the upper body, you can put a weight, or on the body of one side, you keep an arrangement of another extra link, which will stop it from moving away if it tends to move away, and so on. So such a closure is called force closure. Okay. Cam follower often has a force closure. If by self weight, the follower sits on the cam. Okay. At this point, I stop, and in the next lecture, we go into more definitions, more concepts, and then actually a little intensive topics which will come again and again in our actual business. Okay, so see you again in the third lecture. And when I upload this lecture, at the same time, I will also upload assignment 2, and you are supposed to look for it and solve it and submit in due course of time. Okay, thank you.